In this video, I want to talk about RAID technology. So RAID is an acronym for Redundant Array of Independent Disks, were invented to address the problem of disk reliability, cost, and performance. So basically in RAID, data is stored across many disks with the extra disk added to the array provide error correction or redundancy. The inventor of RAID is David Patterson. Garth Gibson and Randy Card provided a RAID taxonomy for persisted for a quarter of a century, and despite many efforts to redefine the RAID technology, nowadays still very popular and used in many systems. There's many types of RAID. The first one we call RAID level 0. So this known as the drive spanning. This provide improved performance but no redundancy. So basically in RAID level 0, data is written in block across the entire array. So we have the array of disks right here. Have multiple disks and each one has the multiple surface. So the data weather report for 14 November partly cloudy with a period of rain and sunny and so on. Okay, so the information basically gonna be striped or divided into several smaller blocks, and each of the block of data gonna be written on a different disk surface. So we see the weather gonna be divided into some part right here, and some part gonna be written into another disk surface right here, and so on. Okay, so you can see that each piece of the information right here gonna be written into multiple disks. So in case one of the disks right here gets crashed, we still have the information from other one. But you can see that once this one disk gets crashed, there's no way we can recover it. So that means the RAID level 0 is no redundancy. With that said, the disadvantage of RAID 0 is very low reliability. However, the RAID level 0, because the data can be written into multiple disks, and the RAID 0 offer very good performance, or the best performance out of all different type RAID and with, for example, with a separate controller and a cache for each disk, RAID 0 is also provide a very fast and very quick write and read performance. And also RAID 0 is very inexpensive. With that said, RAID 0 is basically recommended for non-critical data that require high-speed read and write. For example, the application for video or image editing. So that's the first type RAID. The second type RAID we call RAID level 1. So this is known as the disk mirroring. This will provide 100% redundancy and very good performance as well. So basically, in this approach, too much set of disks contain the same data. So each time data is written into the system, is duplicated onto a second set of drive called the mirror set. So for example, here's the first set right here, file A, and also have another set that's a duplicate of this one right here. You have the file right here. When we write file B, we have another duplication right here, the file B, and so on. So okay, so we can see one set right here, another mirror set right here. So you can see that the performance on dry and up the RAID level 0 is very slow, because every time data written into one disk gonna be also required to written to another disk as well. However, the read is much faster because the system can read from the disk arm that happen to be close to the closer to the target sector. So maybe the disk arm gonna be read from this one or maybe from this one. So this could reduce the rotation latency in a half in on read. So with that said, the duplication structure right here, the race one is very costly. So you need to spend more to make the data is duplicated. RAID one basically is the best suited for transaction-oriented high availability environment, and that with the application, for example, require high fault tolerance, such as accounting or payrolls. That's type application we can use with the RAID level 1. The next type RAID technology, that's the RAID level 2. So the configuration consists of a set of drives and a set of Hamming code drive. So you can see that the here the data driver here. Information gonna be stored into bit level and gonna be written into different disk surface, and that's for data. And also we have a Hamming code drive to for data correction. If one of the information on the disk right here get crashed or corrupted, we can use the information on the Hamming drive to recover the corrupted information. So the RAID level 2 performance is very poor, and the cost is relatively high. Okay, the reason is that the reason is that the Hamming code generation is very time consuming. So every time information written into the data drives, also need to construct the Hamming code for the Hamming drives as well. So this is very time consuming, and that's why the performance is very slow, or RAID level 2 is too slow for most of the commercial implementation. The next type of RAID technology is that we call RAID level 3. So basically, the drive bit across a set of data drive and provide a separate disk for parity. So you can see that here's a different this is to store the information. So in this way, the information gets drive into a bit that gonna be written into different disks. Okay, so for example, you have the high nipple for ASCII of the some data right here for the W right here. So you have 0, 1, 0, 1, and to compute the parity. So basically parity is just the perform the XOR operation on the bit 0, bit 1, bit 0, bit 1. So we get 0. The same right here, we can compute the parity for the second this right here 0, 1, 1, 1. So we get 1, so and so on. Okay, so we can have the parity right here. The idea of the parity right here, we can use the parity to recover one of the disks here get crashed. For example, this one get crashed, we can use the information here, information here, information here, and information from the parity to recover this information bit. Or in case you have this one get crashed, we can use the information here, 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 and here to recover the information here. Okay, so this is very flexible, and so provide the way to protect the information if something gets crashed with one of the data stored in the disk. Basically, RAID level 2 is not suitable for commercial application, but instead it's good for a personal system instead. The next type of RAID technology is at the RAID level 4. So in this approach, the way we adding the parity is just the same with the approach of adding the parity to the RAID level 0. Okay, so basically data is written into block across the data disk. You can see data divided into different blocks, and each block will be written into different driver here, driver 1, driver 2, and 3, and 4, and so on. Okay, and the parity block is written into a redundant drive. So here's a redundant drive, and the parity 1-4 gonna be performed by using the XOR operation of the data on drive 1 with the XOR with the data on drive 2, XOR with the data on drive 3 and drive 4, and we get the parity for from 1 through 4. Okay, the same right here, we can compute the parity for the drive from 5 to 8 and so on. Okay, so for example, one of the drive here get crashed, we can use the information from here, and from here to recover the information here. Okay, so similar to the level 3, but now the information can be performed in terms of block instead of bit level as in the level 3. So RAID 4 basically would be feasible if all the record blocks were the same size. Okay, because we do perform the XOR operation right here, so this one require only the block or driver here need to be the same size. The next one we call RAID level 5. So basically just the same approach with the RAID level 4, but with the distributed parity. Okay, so with the distributed parity, some accesses can be serviced concurrently, thus giving good performance and high reliability as well. Okay, so as you can see here, we have the 4 disks, and we have the information gonna be divided in multiple stripe, and stripe 1 is one piece of information, stripe 2 store one piece of information, stripe 3. And then in the last disk right here, instead of storing information, now we're gonna store the parity of the first 3 disks right here. So it's all stripe 1 with stripe 2, it's all with stripe 3. We get the parity for stripe from 1 through 3. Okay. Now, instead of compute the stripe parity for the next one, we're gonna put right here as the same way we do with the RAID level 4. But now in the RAID level 5, we have the distributed. This means now the parity for the second row gonna be stored in the third disk right here. So we can have the stripe 4, stripe 5, and stripe 6 have the parity stored in the third disk right here, and so on. Okay, so we have the stripe parity from the 7 to 9 gonna store in the second disk, and parity for the stripe from 10 to 12 gonna be stored in the first disk. So you can see that the parity not store not already stored in the single disk, but now it's spread into multiple disks. Okay, so in this way, one of the disks here get crashed, you still have some information from other disks to help the system recover the corrupted information. Okay, so basically RAID 5 is used in many commercial systems, and that's the RAID 5. We can say that it's provide the best read throughput of all parity model, and give the acceptable throughput on the array operation. And RAID 5 offer best protection for the least cost, and that's why it has been used in many commercial applications. For example, it can be used to store the information for the server, like email, database, or web server. Okay, so that's a very popular and efficient way to protect the data, and so have the good performance as well. The RAID level 6 carry 2 levels of error protection over strive data. That's we call read Solomon and parity. So you can see that the information gonna divided into multiple blocks and store the information. Now instead of calculate the parity only, now we have the additional information that's the read Solomon for the second layer to protect the data and to correct the information if one of the information right here gets corrupted. And also here we apply the distributed approach as well. So the protection parity and read Solomon are going to be distributed into different dishes. RAID level 6 can tolerate the loss of the 2 disks, and also it's require a write intensive but provide a very highly fault tolerance compared with other RAID architecture. So the last RAID technology we discussed here, that the double parity RAID, okay, we call RAID DP. So this one employ pair of overlapping parity block that provide linearly independent parity function. So you can see right here that the multiple dishes, and we have the parity gonna be stored in different dishes and also calculate in a different way. So for example, the first parity AP right here gonna be computed by A1 XOR with A2, XOR with A3, and XOR with A4. Okay, so we obtain the AP1 right here. Now we have the double, which means we have another way to compute the value of a that's gonna a function of A1. Okay, so that's we have the AP right here, AP2 right here. So basically AP2 equal to AP1 compute XOR with B2 with C3 and with D4. Okay, so that we obtain the AP2 right here. And then we compute the BP1, so it's gonna be linear in this way. That's gonna row XOR operation of the data on the row B. And also we have the BP2, that's gonna be A2, B3, C4, and DP1. Okay, so that's the way we compute the parity, the information of the parity disk right here. We also have CP right here, gonna be for the row, and also CP2 right here, gonna be by AP3 before CP1 and then D1. Okay, that's gonna be CP2, and also we have this DP1 gonna be for the row from D1 to D4, and DP2 gonna be A4, BP1, C1, and D2. Okay, so that's got a zigzag pattern to compute the DP2. So for example, now if 2 of the disks right here get crashed, we can use the information of the remaining 4 disks right here to recover it. So first of all, 2 of these disks get crashed, so we gotta first only recover A2 first. A2 gonna be recovered by using the BP2, DP1, C4, and B3. Okay, and we recover A2 right here. Okay, once we recover A2, we're gonna using this row to recover A1. And once we recover A1, we're gonna using this information right here, B2, C3, D4, and BP2 to recover B2. We use the A1, C3, D4, D4, and AP2 to recover B2. And once we recover B2, you can recover B1, and then we recover C2, and then we recover C1, recover D2, and recover D1. Okay, so that's the way we recover the information if two of the disks get crashed. So this one very provide a very good performance compared with the other technology of RAID. So here's a few remarks on the RAID technology. So RAID DP can tolerate the loss of two disks, as we discussed before. It can recover a piece by piece, and then the whole information can be recovered. The use of simple parity function provide RAID DP with better performance compared with the RAID level 6. And also because the two parity functions are involved, so RAID DP performance is somewhat degraded or slower compared with the RAID level 5. And sometimes we call RAID DP so with the even odd. So basically that diagonal parity RAID or RAID 5 DP, advanced data guarding RAID or RAID ADG and erroneously RAID 6. So it different name that depend on the manufacturer and so the organization, but they're the same with the technical RAID DP we just discussed before. So basically, a large system consisting of many drive arrays may employ various RAID level depending on the criticality of the data on the drives. So for example, a disk array that provide program workspace, for example, file sorting, does not require high fault tolerance. However, some critical or high throughput file can benefit from combining RAID level 0 with RAID level 1, and also for sometimes we call that hybrids is called RAID 1.0. Also, RAID 5.0 that combines striping and distributed parity for good fault tolerance and high capacity as well. So a higher RAID level do not necessarily mean the better RAID level. It's all depend upon the needs of the application that's use this. So this depend on the application, depend on the reliability, depend on the performance. So we can select the right RAID level for the system we are using. Okay, some information we can find more in the textbook or search through the website for additional information.